So hopefully everybody can see my screen and my pointer.
Yep, it's visible.
Okay. So okay. So thank you for having me at your journal club. So I'm going to talk about some work that we have been doing for the last several years. In fact, although the connection with string theory was found in the last paper. So the title of my talk is From Euler to Veneziano and Back. And please feel free to stop me to ask for clarifications. I sort of kept the pitch quite broad. So some of the stuff may be too simple for you, but in any event, hopefully we'll all be on the same page. So I wanted to ask a question because this may not be familiar to everybody. So the person on the left is a famous Indian mathematician by the name of Madhava, and he lived in the 14th century. Now, I'm not sure whether this is an authentic depiction of how he looked like, but then this is what I found on the internet. And among the many things that he studied were infinite series. And one of the infinite series that he's known for, which is called the Madhava-Leibniz series, is the infinite series for pi. So pi is literally 3.141 and so on. And this is that series. And as you can make out, it's an alternating series. And in fact, because of the 1/n dependence, you can anticipate that this series actually converges very slowly. And there are accelerating techniques to improve the convergence. I'll comment on those things later on, right at the end. And this person here, of course, needs no introduction. He, by some count, is probably one of, if not the most famous or one of the most famous mathematicians of all time, because he was extremely prolific. This is Leonhard Euler. And he lived in the 18th century, and amongst the 25,000 pages of mathematics that he produced, one of the things that he is known for is the zeta function. And the zeta function, when k is an integer, takes on this form. There are analytically continued versions of this as well. So in both these cases, there's a sum from n equal to 1 to infinity. And the question that I'm going to ask is that, is there a connection between the work that Madhava did, so this series, and what Euler did, amongst many other things, the Euler Beta function, which will be a main focus of my talk, and also the Zeta function? Is there a connection between these two? In particular, can the sum over n here be interpreted as sum over exchange particles and scattering? So just to give the story away, of course, you know that the answer is going to be yes, but in what sense is it going to be yes? Can we actually literally see these kind of summons in some problems that we can study? So here is my very poor attempt at an animation. So there is a string that is going, an exchange string. So here it might look like it's going to be a closed string. I'll talk about both open and closed. But the beginning part of my talk, so far as string theory is concerned, is going to focus on the open string case. And this is based on work done with Arnob, who's there in the audience, who's an Inspire faculty in IISc. And we put out a paper recently. It uses a technology that we have been developing with my student, Ahmadullah Zahid, who's a postdoc in ICTP right now. So there were various versions of this work that we did. So the work that I'm going to use is related to something called dispersion relations, crossing symmetric dispersion relations in quantum field theory. But the root of this program that we developed in 2021 has its seeds in conformal field theory. We were trying to understand the conformal bootstrap. So we figured out in this paper, co-written with Rajesh Gopakumar and Hamadullah in 2021, how to rigorously define what is called the Polyakov bootstrap from the CFT context. And another paper that we are going to use is this paper with co-written with a postdoc who's right now a postdoc in Germany. And this GFT actually stands for geometric function theory, which is an area of mathematics. So we are not going to use much of geometric function theory. We are going to use a particular dispersion relation that was worked out here, which will be useful for the open string amplitude. And as I mentioned, that this line of research originated in exploring Wheaton diagrams in conformal field theory bootstrap. So we were interested in calculating critical exponents And this is a program that was, which essentially started in 2017. And if you are interested in a short paper, this may be a good paper to look at. So as an appetizer, let me present for you a new formula for pi. And this can be found in the in the appendix of this paper that I wrote with Arnob. And the formula looks very interesting. It is, of course, an infinite sum. What is interesting is on the left-hand side, you have pi. So this is supposed to be literally, this is an exact equation. This is not an approximation. So this is an exact equation. And you're summing from n equal to 1 to infinity. And in the summand, you can see various interesting pieces. So there is one piece that is kind of reminiscent of the object that you saw in the Madhava series. This 2n plus 1 was in the denominator of the Madhava series. But then there are interesting extra pieces. There is this extra parameter lambda that appears. So n is getting summed over, but lambda is not getting summed over. So this is what is called a parametric representation. So this is supposed to be valid for any value of lambda, so long as the real part of lambda is bigger than or equal to bigger than minus 1. So it is actually supposed to be valid even for lambda complex. So this is some piece that you recognize. And here, this is what is called a Pochhammer symbol. I just wanted to make sure that everybody is on the same page. So the Pochhammer symbol is a ratio of gamma functions. And in particular, it's denoted by some simple bracket with an underscore here. And if the underscore is an integer, then this Pochhammer symbol is a polynomial. So in particular, this object here is a degree n-1 polynomial in whatever appears here. And I'm going to show you that this exact thing appears in scattering amplitudes, in open string scattering amplitudes at special kinematical values. And of course, you can guess what the special kinematical values are, because gamma of half is supposed to be root pi. So if you use the Veneziano amplitude, you're going to get pi somehow. And the new thing is going to be how we derive the right-hand side. Because the right-hand side has this interesting piece, object, that there is this parametric dependence on lambda, and this is supposed to be valid for any lambda that is whose real part is bigger than minus 1. So I will show you some numerical experiments later on in the talk, just to convince you that we can this is indeed pi. The way that this was proved was using the crossing symmetric dispersion relation. So if you actually take this sum and put it on Mathematica, unless and until lambda takes on special values, Mathematica will not be able to do the sum analytically. But you can actually demonstrate that, for instance, when lambda is equal to half, Mathematica can do this sum. You can specify sum from 1 to infinity, and it will produce pi. But for other things, you'll have to carry out either numerical checks, or you have to go through this route via the dispersion relation, which was the origin of the derivation of this formula.
Is there some simplification for lambda goes to infinity or something?
Yes, indeed, that's right. Indeed. So that is what I'm going to talk about. You guessed it right. So lambda, real lambda greater than minus 1 is a free parameter. And I would like to say that this has an interpretation in field theory. So I guess the experts in string field theory in the audience would like to think of this lambda as having something to do with stubs, I suppose. But I'm not an expert in that, so we can have a discussion later on. But I will give you an interpretation of this lambda using field theory arguments as to how it originates when we do field definition in a theory with infinite modes and we do a hard truncation. So I will make all this precise in a bit. And as Michael was asking, this formula does not exist. First of all, the formula does not exist in the mathematics literature. So we have asked around a few mathematicians. We posted this formula on social media. We didn't get anything. And also the fact that the origin of this formula is a little roundabout. That's why we are quite confident that this does not exist in the mathematics literature. And as you were asking, if lambda is much...
Sorry, I haven't... Can I ask it? So
yes.
This formula works for, like you said, it fails certain times for certain values of lambda. Is it,
so if the real part of lambda is less than minus 1, less than equal to if it is equal to minus 1 or less, then this does not work. It does not converge, but you can actually try to work out an analytic continuation, but that is not the purpose of what we are going to do.
I see. So, but like when lambda is real part of lambda is always greater than -1, mathematical can always evaluate, because what worrying me is that like, is there a value of lambda where this poke hammer symbol truncates, the ones that is higher term just gives you 0?
No, that is not
Or-
possible because of the Pockhammer symbol. You
That
can
is
get
not
some zeros, but it does not become 0 everywhere else. That's a very valid point,
I
but
see.
the Pockhammer symbol does not truncate that way. Yeah,
Okay, good.
that's a
Thank
valid
you.
point. Yes. And as Michael was asking, if lambda is very big, then the summand. So you just pretend that you're truncating the sum, and you look at the summand, which is not mathematically a rigorous thing to do, but let's do it anyway. You can expand the summand around lambda infinity, and you literally get the Madhava series. So whatever you got there in the previous slide that I showed here, you literally get this series. So in that sense, this formula is an interpolating formula between the Madhava series and what I'm going to demonstrate are faster converging quantum field theory inspired ones. So the takeaway, in case I lose my audience in the middle, is that although this is not a folklore amongst this audience, because you guys think about string field theory more in the language of field theory, is that if you include one massive higher spin particle, then you need to include all of them. So in what sense is this a statement? Is this a correct statement? We will re-examine this, and whether it makes sense to truncate, do a level truncation in the 2 to 2 scattering amplitudes as a sum over levels. And we know that field theory has been the guiding beacon in high energy physics for the last several decades. And can we use field theory insights to get new string insights? And where I am coming from, because my interest or the overarching motivation into getting into this program was from the S-matrix bootstrap or the conformal bootstrap. And I won't say anything much about is that, of course, we know that string theory is yet to make contact with nature. And maybe we need to understand the non-perturbative structure using string field theory techniques. But in the meantime, can these other sort of limited ways using dispersion relations, using some modern version of the dispersion relations help in exploring these kind of stringy physics? So the punchline is going to be that we are going to use a new kind of dispersion relation to find a new quantum field theory inspired decomposition of conventional string amplitudes and the Euler Beta function. And this, in turn, as mathematical corollaries, will lead to quantum field theory like representations of pi and zeta functions. So here is an outline of my talk. So I will begin with a field theory background, and so we are going to talk about EFT in some slightly different way, not in the language of the Wilsonian way of thinking about EFT, but we want to think about it from the point of view of a truncation. And then after that, I'm going to talk about dispersion relations. And there are two kinds of dispersion relations. The conventional one, which is popular in the literature, is what is called the fixed T dispersion relation. And then I'm going to talk about the less familiar one, which is the crossing symmetric dispersion relation and the local version of the crossing symmetric dispersion relation. So I'll make these terminologies precise because these may not be the way that these words local is used in other areas. So I will need to explain what I mean by local. And then I'm going to exhibit a new formula for the Euler Beta function, expanding in mass levels, and discuss truncations. And then show you numerical experiments where I'm going to show you how to calculate pi up to 500 decimal places using this. We can do to any decimal place, 1000 decimal place. It's just time, that is it. So the Euler Beta function, of course, is somehow naturally connected with open strings. Then I'm going to discuss the closed string briefly. And then I'm going to go out of my comfort zone and pretend that I'm a string field theorist, and I'm going to discuss the string field theory status for the closed string and open string, where I'm hoping that the experts in the audience will chip in and correct me if I make wrong statements. So let's begin with some essential physics, and this will be something I kept this part just to be pedantic. and have some pedagogical elements in this talk. So some essential physics is how we usually approach QFT. So at least the way that we approach QFT is through effective field theory. And the picture is that you have some spectrum of particles. So there are some low mass particles and some high mass particles. And of course, in your accelerators, you cannot go to arbitrary energies. So presumably you cannot excite all the modes that go off all the way to infinity. And the way that we actually think about particle physics is we put in the information about particles that we see in scattering experiments and build quantum field theory with those. And then we examine various consistency conditions like unitarity and so on and so forth, and see whether we need extra particles to restore unitarity. So what we do is we start off by writing down the Hamiltonian for the low mass particles, and this description is supposed to be valid at energy scales comparable to these masses. But of course, we don't literally throw away all these extra particles that are there. If we know about them, what we do is we integrate them out. But of course, if we don't know about them, there is no reason to put them in. But if you integrate them out, the effects are felt in the low energy description. And if you don't know what these masses are, you can use a dispersion relation, and which uses some information about what is going on at high energies. And using these dispersion relations, you can actually put bounds on the Wilson coefficients. So that is how we think about effective field theory in this language. But we need to understand the difference between truncation and integrating out, because what we are interested in is to truncate. So we want to truncate the sums that we saw up to some n. So basically, we will throw away many higher spin modes, an infinite number of higher spin modes. So we need to think about what effect that can have. So let's consider a toy example. And because I will be focusing on the Euler Beta function, I want to cook up a quantum field theory where you just have two channels. So let's cook up a quantum field theory where you have phi1 and phi2 to be massless scalar fields, and psi1 and psi2 to be two heavy scalar fields with masses m1 and m2, such that m2 is much bigger than m1. So I just wanted to have two heavy scalar fields. This is not strictly necessary, but then to make my point, I will use these two. And for simplicity, let their interactions be described by some cubic couplings. So phi1, phi2, massless times heavy, and then lambda 2, phi1, phi2 times psi2. And let's consider 2 to 2 scattering, phi1, phi2 going to phi1, phi2. So you will get tree-level amplitudes in this particular case because of the Lagrangian that I've designed. The T channel is going to be absent, and you will get just the S and U channels, and you'll simply get this answer. And this is supposed to be crossing symmetric, invariant under SU interchange. And of course, if there are any students in the audience, you can cook up a Lagrangian that leads to 2 to 2 scattering of similar kinds with the U channel absent. So now say that we are interested in values of the energies S and U, both much less than m1 square and m2 square. Then what you would do is that we would just Taylor expand the above formula, and then you will get a bunch of contact terms. So these are contact terms because you have Taylor expanded, the information about the exchange is kind of hidden. And so you'll get something that has a constant, and then you'll get polynomials. And the polynomials that you get by doing this Taylor expansion is indicative of a local theory, the fact that the interaction range will be in a limited regime. So this first term here, that is here, is what would arise if you added this extra term, phi1 square, phi2 square, and this is a kind of a contact interaction, while the second term would arise if you had a derivative, phi1 derivative phi2 all square. And just to emphasize, this effective description is only valid for low energies. And so now you can ask the question, so let's crank up the energy. So let's not focus on low energy. So at first level, let's consider what happens if your energies are a little bit above m1 square. So you can no longer ignore the m1 square pole, but you can expand the second piece, which is m2 square. So that one you can still do a Taylor expansion. And so what you can do is you can choose some reference point and expand around this point. And this is how you proceed in the conventional sense when you think about effective field theories. But this is not how we would like to proceed. We will refrain from such expansions. It's something that you can do, of course, but then rather what we are going to focus on is what happens when you consider a truncation. So this is where a subtle issue shows up. So let's imagine that we start off with the original Lagrangian and do a field definition. So for example, let's consider a very specific field definition. The heavy field psi2 goes to psi2 plus alpha 1, phi 1, phi 2. And you start off with the original action, and if you did this, then the new action will look a little messy, not terribly messy, but a little messy. And in this, with this new choice of fields, we would generate a contact interaction, which would be proportional to this parameter that I've introduced here, alpha 1, in doing this field definition. And this would generate a contact interaction. Now you can do this exercise. This is something that is usually given in a first course in quantum field theory to show that with this new Lagrangian, if you did phi 1, phi 2 going to phi 1, phi 2, then you will get exactly the same answer that you get using the previous Lagrangian. So just to point out that this particular contact interaction is actually cancelled by an exchange term at the same order. Now, you start off with this field-defined Lagrangian, and now let's throw away these heavy fields. So let's throw away psi2. By throwing away, I just delete by hand any term in the Lagrangian that has got psi2. Then this new Lagrangian would be this alpha 1 parameter that I introduced while doing this field definition. This alpha 1 would show up in the results of the calculations of the amplitude that I would do using this new Lagrangian. And this would mean that the contact terms in my example lead to ambiguities. So field definitions will not change the residues at the poles, but the contact terms will be ambiguous in truncations, while the residues at the poles will not be sensitive to this ambiguity. So is this part clear? Because this is going to be essential later on as well. So this means that if pi, for instance, has a field theory way of looking at it, then the truncated series sum must have at least one parameter ambiguity in it. So I don't really know how many parameter ambiguities can be there, but then at least it should have one parameter ambiguity. And the same thing can be said for zeta k. And same thing can be said for the Euler Beta function, because that is the motivation that the actual representation should actually at least have one parameter ambiguity. And the second thing to remember as a lesson from this exercise is that this ambiguity should be associated with the polynomial or regular pieces only, not the exchange pieces. So exchange pieces I'm defining in a very particular way. I literally mean residues over poles. So I don't mean that, so if the residue is at s equal to n, then, if the pole is at s equal to n, then I don't mean that the residue will have some s dependence. That would be a part of the contact term in my way of thinking about splitting the Lagrangians. So once you have this ambiguity, then how do you make use of this ambiguity? Is it of any use, or is it just some kind of a red herring and we somehow need to get rid of it? So I'm going to argue that this ambiguity is very useful because after all, the exact answer is not dependent on this ambiguity. So you should get some, when you do a truncation, you should get some equation that looks approximately like this. So this is some observable and you're working with a truncated answer. So the partial derivative with respect to this parameter lambda should be at least approximately 0. And what is going to turn out to be the case is that for a given value of the truncation of the series n max, this will determine the range of lambda where this equation is approximately true. And it will turn out that this range of lambda where we see plateaus as a function of lambda will predict the true value. So even if you did not know the exact answer to start off with, if you ask me to predict the answer, then this is what I would do. I would look for plateaus in these observables, and I would be able to tell you what the true value is. And it turns out that without this lambda, it will be difficult to have a truncation which captures the essential features of the string amplitude. And I'll give you some examples of that later on. So put differently, lambda enables us to identify a suitable Lagrangian. And just to keep you interested, I will explain this when I discuss Steve Giddings' 1986 paper, where he used Wheaton's open string field theory to get the Veneziano amplitude. So just to carry on with this pedantic nature of this discussion, so of course I said that the residues are somehow sacred, but the contact terms can be moved around. So there's some redefinition ambiguity associated with the truncated Lagrangian. So how do we use these residues? The residues are used because of the fact that although you are at tree levels, you have poles, and the simple poles actually have discontinuities. So if you so suppose you consider the simple example f of x is 1 over x, then you can work out the discontinuity of this pole. It is just proportional to a delta function. So the proportionality constant is some 2i pi factor. And the discontinuity is what we are going to make use of, because the discontinuity is going to enter the dispersion relation. So the role of the dispersion relation is going to be to fix the contact terms, the regular pieces in the amplitude, using the information about the discontinuity which do not have any ambiguities. So this is the question that we will address. Can we use the poles to construct the full amplitude? So the more involved,
this is classical amplitudes, right? Because if you have a loop amplitudes, then you will also have branch cuts.
That's right.
So
yes. Yeah.
How will you deal with?
You can. So the dispersion relation that I'm going to talk about can handle loop amplitudes because of the fact that you can have massless exchanges. There might be some prescription that you might have to use because the cut will be all across the real axis. So once you give me that prescription, or once we work out the prescription, then you can use the dispersion relation.
I see. So it also works for the information coming from branch cuts.
Yes. Yeah. So the more involved way to understand how to use this discontinuity is, of course, to use unitarity. Why this discontinuity plays a role is just the fact that you want your SS dagger to be equal to 1, and that relates the imaginary part of your T to the T times T dagger. So you get some pictorial equation of this kind, where the imaginary part of the tree level is related to the product of two 3-point functions. So to constrain contact terms, we need some more input, and this is where dispersion relations come in. And just before I delve into dispersion relations, let me restate the problem using mathematics. So I will restate the same problem by stating it as a problem in complex analysis. So what is the problem that we are trying to solve? So we have a function of two variables, s and t. And I'm going to use a sort of a very restrictive example here. So suppose you are given the residues in the variables s and t, and the problem is that you are supposed to determine a function that has got the correct residues. So for example, suppose we have unit residues at s equal to n. So all s equal to n for n equal to 1 to infinity have unit residues. And also the same thing for t equal to n. Then the first temptation would be to write down an object that looks like this, summation n equal to 1 to infinity. 1 divided by s minus n. 1 is because I told you that the residue at s equal to n is 1. And immediately you would stare at this object and realize that this is nonsense because the n sum does not converge. And so you could try to fix this by having a better n sum convergence behavior. So the rule is that the residue at s equal to n is still 1. So you could actually multiply this, say the s channel bit here, by s by n. And since you are evaluating it at s equal to n, the residue is still 1. And the second guy, again, you do the same thing. And then you get a function such that it converges as a sum over n. And this is what is called the Mittag-Leffler theorem. So here, of course, is a cooked up example because I did not have to talk about s and t together. The way that I have set up this example, I could have talked about the s dependence and t dependence individually because they are not coupled. So the only thing that you have to specify is what is happening at high energies, because obviously, if I thought that this is a valid function and I looked at what is happening for s very large, I would naively say that at s very large, each term goes to a constant. And if n is if this n sum converges, then the amplitude should be a constant. Whereas in this new way of fixing the residue, where I've multiplied by s by n, the amplitude actually goes to grows linearly with s. So if you specify what the high energy behavior is, then I could recreate this function. The problem arises because this is a function of two complex variables, s and t, and then there is, in general, there's a coupling between the s and t variables, which happens via the residues. And the general solution given particular residues which depend on other variables is not known, at least the general way of thinking about this. And these are related to, if you search for, Google search for cousin problems in maths, this cousin is not your cousin and my cousin. The cousin is the name of a person, and these are called the cousin problems in mathematics. So then we have to devise a way around, because you would have thought naively that if I knew the residues, if I knew the poles, then I should be able to write down an expansion of this kind, but clearly that is not true, and the Euler Beta function is a good example where it is not true. So the question is, how do we then constrain the contact terms? This is where dispersion relations come in. So before I delve into dispersion relations, are there any questions? Okay. So there are no questions. So let me delve into dispersion relations. So dispersion relations are nothing but a fancy way of applying Cauchy's residue theorem in a clever way. So imagine that you are given a function f, and somebody tells you that there is some information about the discontinuity of the function. So there is a branch cut along the real axis. So this is what Firat was asking, that what happens if you have loop diagrams. Then what you would do is you would start by drawing a small circle around a point where you want to use Cauchy's residue theorem and write down a formula for f of s. So this is what you would do. So this is just Cauchy's residue theorem. And then you would just deform the contour. You would actually make it wrap around the cut and also go to infinity. So what you would get looks like this. So you have a contribution from the arc at infinity plus the line integrals along the red lines, which essentially pick up the discontinuity of the function across the branch cut. So what happens is that if we can throw the arc at infinity, so the function has to die off sufficiently fast enough so the arc at infinity can be thrown away, then we can recreate the full function, both the real and imaginary parts, by just knowing the discontinuity of the function in the complex plane. That's the idea of a dispersion relation, that just by knowing the discontinuity, so in the language of the tree level amplitude, you just need to know the residue at the pole, and then you can recreate the full function anywhere in the complex plane, provided you knew the fall off at infinity. So there are a few subtleties. Subtlety one with an easy resolution is what if the arcs don't die. So if the arcs don't die, that has got an easy fix. What you do is you simply change the starting point. You start by considering a function f of z divided by some z minus z naught to some power. It does not even have to be z minus z naught. So suppose you wanted to divide by 3 powers of z, you could have 3 different versions of z naught. So z minus z1 times z minus z2 times z minus z3. The penalty that you're paying here is that you are introducing some subtraction constants, which are completely up to you to choose. So you can choose your z0 to be whatever you want, z1, z2, z3, whatever you want, which essentially means that the function value at z0 or whatever, wherever you have introduced the division, will now enter the game. So this is somewhat analogous to renormalization in the sense that to remove infinities, we supply experimental inputs. The subtlety 2, which has a non-trivial resolution, is that the amplitudes that we are interested in will have at least 2 channel symmetry. So in the examples that we have been focusing on so far, has ST interchange symmetry. And the amplitude of interest is invariant under ST interchange. We are just focusing on tree level amplitudes, just to remind you. So how do we write down a dispersion relation now? Because now we have 2 complex variables. And whatever I showed using Cauchy's residue theorem has one complex variable. So conventionally, what you want to do is you want to recycle whatever you did for the one variable case. And if you want to do that, you have to hold one of these two complex variables to be fixed. And conventionally, you hold t fixed and you write down a dispersion relation as a function of s. So this is what is called a fixed t dispersion relation. But as should be clear to you, this breaks crossing symmetry. So crossing symmetry you have to impose separately as constraints. So crossing symmetric dispersion relations, you now might wonder that can we have a version of the dispersion relation which manifests crossing symmetry? So it manifests somehow the Feynman diagram-like picture that we have in quantum field theory. So crossing symmetric dispersion relations were historically never in the forefront of research. And to build such a dispersion relation using single variable Cauchy residue theorem as a starting point, we have only one option, and the option is to forego working with the Mandelstam variables, at least at the onset. Otherwise, you won't be able to write down a dispersion relation in a single variable because you will always be holding the other variable fixed. And because of this thing that you have to work with some other variables which are not the Mandelstam variables, this was probably the reason why they were not really in favor. And the most useful paper that we found was an old paper from 1972 by Oberson and Khoury. When we located this paper, so we were working in 2020 during the lockdown. We were trying to give a rigorous derivation for the Polyakov bootstrap. And when we located this paper only had 8 citations. And another thing is if you open this paper and if you try to see if any of the formulas look anything remotely familiar to you, you will find that the most useful thing was added as a footnote somewhere. And so that is why it really needed a careful read to get the really useful information out of this paper. And the logic is the following. So logic is that you make a suitable change of variables from st to say z and a, where a is a crossing symmetric function of s and t. Now there are whole bunches of crossing symmetric functions that you can think of, and we'll think of a suitable one, a simple one. So the logic is that we are going to hold a fixed and then write down a dispersion relation in z. And for the two-channel case, there is a simple natural choice for A. This is something that we argued in this paper with Prashant Raman, which I cite here. The simple natural choice of A, it looked natural to us because this was the natural extension of what Oberson and Khoury had done, is that you take the crossing symmetric quadratic invariant and divide it by the crossing symmetric linear invariant. So because you have two channels, you don't have the constraint s plus t plus u equals to 4m square that you usually have from kinematics. So, and I should point out that I am using S1, S2, and S and T interchangeably. So if you see S1 and S2 in any of my formulas, you should, in your mind, interchange them with S and T. So then we churn out the mathematics. So in this original, yeah.
Can I ask a question? Why is for example, why is regular limit is not a natural one in this context? Like, say I choose A to be S over T or T, T over S, something like that.
You want it to be crossing symmetric. So the point is that S over T.
So that doesn't work.
No, because S over T is not going to be crossing symmetry. Crossing symmetry in my language means it should be invariant under ST interchange. So if you're using S over T, same. Yeah, it should remain the same under ST interchange. Yeah.
Thanks. I missed that.
Yeah. So then you plow through the algebra. So the thing is that so the essential mathematics is very easy to state. You want to write down a parametric relation between S, Z, and A. So S in terms of Z and A, T in terms of Z and A, such that this constraint holds, because we're going to hold this fixed. And then we're going to write down a dispersion relation in Z. So that is what the goal of this exercise is. So you can find that out. So I'm not going to go through the details, but after you do the algebra, you work out a dispersion relation in terms of Z. You can always transform back to SNT variables. And when you transform back to SNT variables, the resulting object looks very nice. So this is an object, as I told you, I'm going to use SNT and S1 and S2 interchangeably. So this is the amplitude. And this is given in terms of, so because of the fact that the amplitude that I am interested in has a particular fall off at infinity, it does not die at infinity. It goes to, so the little o of the amplitude as s goes to infinity behaves like little s. So that is why you need to introduce these subtractions that I talked about in the usual dispersion relation. So this m00 is basically indicative of the subtraction that we need to do. And then you have an integral to do. And the integral actually looks very interesting because you see, this is something, it has got two pieces. So one of them is the discontinuity, which is given by curly A. I will explain what the notation means in a bit. But the second piece is the kernel. And the kernel should remind you of what you see in cubic theories. So you can actually write it, your sigma you can think of as an m square that you're integrating over. This m square variable is a continuous variable and you're integrating over all that. And S1 is literally like the Mandelstam invariance. So if you can split it up into partial fractions and you will get something that looks like a cubic theory and plus a constant term. So this literally has this picture that you have a cubic interaction and a constant and a quartic contact interaction. And the absorptive part, so what is the absorptive part? So the absorptive part is that suppose you knew the function or you had some information about the function. This absorptive part is basically nothing but the S-channel discontinuity of this function, or here the S1 discontinuity of the function. So imagine that you have in mind the Euler Beta function. So the Euler Beta function has gamma of minus S1. So it will have an infinite number of poles in the S1 variable. And each of these poles will look like a delta function. So in that language, this curly A would be a sum over delta functions in S1. And of course, the residues will depend on S2. So what this absorptive part in this formula is telling me to do is that you don't literally think of S2 as S2, but you replace it by this new object here, which is a combination of the integration variable. So sigma is getting integrated over, and this A, which I'm holding fixed. So A was this ratio of ST over S plus T. So this is the final version of the formula. So is there any clarification that is needed here at this point? Okay. But there is a final subtlety. And the final subtlety is that my choice for A, the variable, the crossing symmetric variable that I'm holding fixed is ST over S plus T. And now suppose you expanded the integrand around A equal to 0, then because you're expanding around A equal to 0, you are going to see polynomials in A, but polynomials in A would actually mean that you get negative powers of S plus T. And in a local theory, you do not expect to see negative powers, at least you don't expect to see S plus T to the power 50, for example, in a local theory. So that's my definition of what I mean by a local theory, that you don't have these negative powers of S plus T. And indeed, this is what happens even at tree-level string theory. You don't see, when you actually expand, you don't see negative powers of S plus T. So expanding around A equal to 0 is basically just setting S equal to epsilon, T equal to epsilon, and expanding around epsilon equal to 0. So the fact that you don't get these negative powers gives rise to additional constraints. What you could do is that you could subtract off these non-local terms or these negative powers, and operationally it would work just fine, except that there was some very nice development which is going to enable me to get analytic formulas much more easily, which is that last year, a statistical physicist by the name of Chao-Ming Song, who's now a good friend of mine, in this paper, he built on our work and helped us find a local compact dispersive formula, which automatically throws away all these non-local terms. And that formula is something very pleasingly simple. It essentially amounts to replacing the second argument in the discontinuity of the absorptive part by st by sigma, or s1, s2 by sigma. So just to go back, so this is what the absorptive part was, and the problematic part was this variable a. You expand around a equal to 0 and you get all kinds of powers of a, and that would translate into negative powers of s plus t. But now the new formula is that you take this guy and you just replace it by s1, s2 divided by sigma. So now when you expand around s1, s2 equal to 0, you'll only see polynomials in s1, s2. So the local crossing symmetric dispersion relation generates for us a non-perturbative Feynman diagram-like representation. So that is the use of this local crossing symmetric dispersion relation. And all these machineries did not exist till last year. So the final thing that we needed to actually come up with a new formula for the Euler beta function would be using this local crossing symmetric dispersion relations. These machineries did not exist till last year, and as a result of which, presumably because of this, we weren't able to develop such a formula. So these physics inputs bypass the roadblock in mathematics that prevented the development of a new formula for the Euler beta function, which makes the poles in both the channels manifest. So the representations that are there conventionally, which I'm going to talk about, I'm going to review in a bit. The conventional ones that you are familiar with do not make the poles in both channels manifest. Okay, so I'm going to take an interlude and tell you something about some fun mathematical facts. So before that, are there any questions about the background?
I had a small question. So you introduced these z variables, but I don't remember if you have written somewhere how it is written in terms of SNT.
Yeah,
or
so
it is
I
not really
skipped that
relevant.
part. You're absolutely right. So I skipped that part because I actually changed the variables back to SNT. So Z in the 3-channel representation actually involves a parametrization in terms of the cube roots of unity. So it's there in my papers, but it was some I did not want to complicate matters, so I did not have the formulas there in my slides.
Okay, but there is a formula which
Yeah,
you
there is
use
a
to
formula.
derive everything, and then you just go back to
Yeah.
SNT, right? Okay.
Yeah, that's right. Yes.
Thanks.
So let me tell you about some fun maths facts. So one fun maths fact is that, of course, I guess many of you must have played this memory exercise when you were kids, or even now, that you memorize pi to 10 decimal places. So I don't know, maybe you can tell me how many decimal places you remember. So I asked one of my school friends, and he said pi was 22 by 7. So I immediately stopped the conversation after that. But to get pi to this 10 decimal place accuracy, using the Madhava-Leibniz series, you require 5 billion terms. And Zeta 2 has this formula as well. So Zeta 2, just to remind you, is pi square by 6. And this is the value of Zeta 2 to 15 decimal places. And to get this accuracy using the Euler Zeta definition, which is the sum over 1 over n square, needs more than 25 million terms. And there's a similar story, although the number of terms needed is not as big as 25 million for all Zeta k's. So Zeta k's, of course, will have better and better convergence properties as you keep increasing k. And just as a background maths facts, I guess this must be known to most of you, that Zeta 2, so the problem was that Bernoulli, one of the Bernoulli brothers, who was Euler's tutor when he was a young kid, he had in the 1680s assigned this as a problem to the then mathematicians, that find a closed form expression for sum over 1 over n square, which of course Euler solved, and he showed that it was equal to pi square by 6. And of course, nowadays, I don't know whether you do that, but then sometimes we actually set this as an exam question for first year undergrads. And of course, another fun fact is that the reciprocal of Zeta 2 measures the asymptotic probability that two integers are co-prime, and a similar probabilistic interpretation for all the integer zetas are available. They measure so k integers, whether they are co-prime or not. Now, there are beautiful formulas that speed up convergence. There are techniques which actually accelerate convergence. So there is something called the Shanks transformation, or there is something called Euler transform, which actually accelerates convergence. So essentially, the Euler transform regroups the infinite series in a certain way. But we don't want to do that because we want to retain this interpretation of n in that summation as a physical object, like a string mass mode or mass level. So we don't want to regroup terms because then that beautiful picture is going to be lost. So we want to use the same picture that we showed, the same series, and our new formulas which were motivated by quantum field theory will give the same accuracies above that I display above using roughly 30 terms. And I'll make this precise. I have some tables and I'll have some mathematical demos. And we will see the connection with massive higher spin particles in the process as well, which of course you can already anticipate. So what is known about the Euler beta function? So this was introduced by Euler in 1730s. The exact date is a little controversial, so one has to look at the Euler archives. I believe it was 1729. I remember that date because 1729 is also what is called the Ramanujan number. And so this is the beta function. So I'm going to exhibit it using negative arguments because my poles are going to be at positive integer values. And as you all know, this is given by an integral from 0 to 1 of this object, which of course now has an which you know that has an interpretation in the language of the string worldsheet. So you also know that in order for us to get a number from this integral, you really require to specify the real part of S1 and real part of S2 to be suitable in the suitable regime. Otherwise, this integral is going to give you infinity. Alternatively, you can actually work out an analytic continuation of the integral, but that is, of course, not straightforward unless, not usually straightforward. So what you can do is you can binomially expand this 1 minus z piece, so around z equal to 0. Or more accurately, if you don't want to do this for mathematical reasons, you can actually use a fixed S2 dispersion relation. And you can reach the familiar single channel pole expansion that you are mostly familiar with. This is also there in Green-Schwarz-Wheat in chapter 1, for example. So you get a pole in, you sum up the poles in either channel, either S1 or S2. And this is supposed to give you the beta function. And of course, the sum over poles has a limited domain of applicability. The sum over pole does not converge unless the real part of S2 is less than 0. And similarly, the second, the T-channel representation needs the real part of S1 to be less than 0. And this, of course, I don't need to tell you, this is what is called duality in string theory. So if you took this truncated amplitude, you would actually miss important information like the high energy behavior. So suppose I just truncated to 10 terms or 20 terms, then of course it would have really bad high value of S2 behavior. Or if you took this series and you truncated to 20 terms, the highest term would go like S1 to the 20, and then this would actually give the wrong high energy behavior. So just to remind you, of course, this is all familiar to you. The Pochhammer symbol is also called the rising factorial. So a subscript n is just a product. So a times a plus 1 times a plus 2, etc. It's a degree n polynomial. N negative also makes sense. So n negative actually gives you poles. So if you have a with minus 1 as a subscript, you get 1 over a minus 1. With minus 2, you get a sum of 2 poles and so on. Yeah. Now, this is something that probably is less familiar, but this should have been known in the 1970s. So there is another way of thinking about this Euler beta function. So instead of the conventional 0 to 1 integral, actually there is another representation where it works in 2 steps. I can tell you the 2 steps later, but then you get another representation where the integral is from 0 to 1, but of a different integrand. So in this particular integrand, actually now the S1, S2 interchange symmetry is manifest. So in the original formula, the S1, S2 interchange symmetry wasn't manifest. Here it is manifest. So you could start off with this representation, and then you could do the same thing. You binomially expand around y equal to 0, integrate term by term, and you'll get a new series where actually now you have poles in both channels, S1 as well as S2, dressed by some Pochhammer, some polynomial. But this also requires some domain of convergence to be specified. The real part of S1 plus S2 should be bigger than -1. So this should have been known in the 1970s, but at least the string theory books don't make any mention of this. But this formula also is not terribly useful because we are working with tree-level amplitudes and we want to claim that this is like quantum field theory. And in quantum field theory, we don't really expect any singularities except at the poles. Whereas here you would get singularities whenever real part of S1 plus S2 is bigger than -1. And just to not become too serious, there is another fun application of the beta function in sociology, which is called the preferential attachment process. And the definition of preferential attachment process raised alarm bells in me. A preferential attachment process is a class of process where some quantity, typically some form of wealth or credit, is distributed among a number of individuals or objects, but in a specific way, according to how much they already have. So those who already are wealthy receive more than those who are not. So this actually sounds like capitalism to me, but let's go back to business. So we are going to look at the Euler Beta function using the crossing symmetric dispersion relation. So we look at the local crossing symmetric dispersion relation. So there is this absorptive part. You're integrating over the first variable, and the second variable is just S1, S2 divided by the integrating variable. And so the absorptive part is just going to be a sum over delta functions. So this is very simple. Once you look at the formula, you can actually work it out what it is going to look like. And for simplicity, I'm going to focus on massless external scattering. This can all be also extended to the tachyonic scattering, so in bosonic string theory, but we are going to focus on the superstring case. So that's why we're going to focus on massless external scattering. So and we're going to derive a new formula for the Euler Beta function. And the steps are, we use the new dispersion relation and find a QFT-like representation for the generalized Euler Beta function. So first we get a generalized Euler Beta function. So all that we have done is we have put alpha instead of, so the usual Euler Beta function is when alpha and beta are both 0, but we have stuck in an alpha and beta, so alpha in the numerator and beta in the denominator. This is still invariant under S1, S2 interchange. And we stick this, we work out the discontinuity of this function as a function of S1. We stick into our crossing symmetric dispersion relation, and this gives you this very nice formula. So you might think that this is ugly, but then this is actually not. It gives you this nice formula, which actually has the poles in both variables manifest. It also has this ambiguity manifest, and I will tell you where this ambiguity comes from, because this is not obvious from the dispersive formula. But I wanted to actually tell you that if you just worked with this kind of generalized Euler Beta function, you're not only going to get some kind of a Pochhammer, but the argument of the Pochhammer here is not necessarily going to be an integer, unless and until alpha and beta take on specific values. So remember that the Pochhammer becomes a polynomial only if this argument, the subscript here, is an integer. And on top of it, it is dressed by some sign factors. So obviously the sign factors will have an infinite number of S1, S2, if you expand around S1, S2 equal to 0. So unless and until alpha and beta take on very specific values, you're not going to get this form of poles dressed with polynomials. So the way that this was derived, this formula was derived, was to use this S1 discontinuity on the left-hand side, plug into the dispersion relation, perform the joint shifts, these joint shifts below. And this is important because these joint shifts of the parameters and the S1, S2 Mandelstam variables leave the left-hand side invariant, but they don't leave the right-hand side invariant. And that is why lambda dependence shows up. So this I already mentioned, that you have the sign dependence and also the argument of the Pochhammer, so the subscript of the Pochhammer, and unless and until you have specific values, you're not going to get a polynomial. And so if you don't get a polynomial, it is not going to mimic what you would expect in out of tree-level quantum field theory. So let's focus on the specific choices where where you get this form where you have poles times polynomials, because that is what you would expect on general grounds in quantum field theory. So the first formula is a representation for the Euler beta function itself. So the Euler beta function now can be expanded in terms of the poles in both the variables, including this lambda dependent object, and dressed by a polynomial. And I should point out that the forms here somehow are so symmetric. So this is 1 over S1 minus n, 1 over S2 minus n, and then this is somehow almost looks like another channel with some wrong signs. So you can think of some lambda as some kind of an auxiliary variable. So when you integrate or when you actually sum over all the modes, the dependence goes away. So you could visualize that there may be some auxiliary field which corresponds to this lambda. Maybe there is a deeper way of thinking about lambda. And you could ask, can we, once we have this representation, can we rewrite this as arising from some Lagrangian, which has this picture that you have cubic vertices, which has phi with higher spins and contact terms. And the contact terms would come because you're expanding around. So these are polynomials. So you can actually rewrite the summand as residues over poles plus polynomials. That is exactly the form that this summand has. And you could ask whether this could be reinterpreted in the language of this picture. Now, there is a small subtlety here, and for massless scattering, you see that n equal to 0, there is a massless pole, but there is a subtlety, and this is a big subtlety because if you think about it, for massless scattering in string theory, in superstring theory in particular, you don't see the Euler beta function. What actually you see is something that is almost like the Euler beta function, but it has a 1 in the denominator. So why don't we see this precise Euler beta function when we scatter massless particles in superstring theory? So what happens is we would like to write it in terms of this Lagrangian. And so we would expect that if we truncate in the number of modes, we would also truncate in the number of spins. And also we would have a finite number of contact terms. If we had an infinite number of contact terms, infinite number of derivatives, then that would not be something that we would generally expect in quantum field theory. So in particular, the form of the contact term should literally look like polynomials in S1 and S2. And the coefficient in front of these polynomials should be finite. So what happens is that if you wanted to actually express it in that language, you start off with this explicit formula that we have. And then you will find that the coefficient in front of these polynomials for this particular case do not converge. And that's the reason we do not see this precise form in superstring scattering. But of course, the fix is known to us. A small modification does the job and does the job uniquely. So we could again start up with this generalized Euler beta function, set alpha equal to 0 because we want a massless pole. And then the question becomes that what are the allowed values of beta? Now it turns out that the allowed value of beta is there is only one allowed value, and that is 1, exactly 1. And this is exactly what you see in superstring theory. So in superstring theory, you get this form. So imagine that you are scattering gluons, then this would be dressed with some extra factor which would look like T8. So T8 is some space-time tensor times trace of f to the 4. So there's some gluonic fields whose indices are contracted in some way. And that is multiplied by this object. And that is the form that you see in superstring theory. So this has this expansion. So this is again manifestly, it has poles in both the channels. It is dressed by the polynomials. And now if you do this exercise, you write it in the language of cubic vertices plus polynomials and ask what the coefficients of these polynomials are. You'll find that now it converges and everything is fine. So this does admit this kind of a picture. So if you want stringy physics up to some energy scale, we want to truncate up to some mode, say, suppose we were interested in trying to analyze what is happening when the absolute value of S1 is less than, say, 10. an absolute value of S2 is also less than 10, then you would actually want to truncate up to 10 modes, because the other modes, what role would they be playing? So if this was an honest to God quantum field theory, they wouldn't be affecting the physics that much. They might affect a little bit, and that has to do with the accuracy with which you want to reproduce the physics. But this formula actually enables you to truncate and enables you to work out or design a Lagrangian with a suitable set of contact terms, and it enables you to truncate in the modes. Okay, so this is going to play a key role in what I'm going to talk about next, which will be working out some interesting formulas. So one thing that you can do is you can work out a generating function of the zeta function. So this is just a low energy expansion of this Euler beta function. And this gives you the generating function of the zeta function. And this actually has this very nice representation again. And the generating function of the zeta function is given by the low energy limit of the scattering amplitude. So for example, you can read off zeta 2 from here. This by definition is 1 over n square, but you have this new representation, which is supposed to be valid whenever the real part of lambda is bigger than -1. And this is again going to give you zeta 2 for any choice of this kind. Now, suppose you wanted zeta to 10 decimal places, then what is the optimum truncation that you can use? What is the lowest number of n's that you can keep? That is where lambda plays a role. To answer that question, the rate of convergence is actually governed by lambda. And just as an aside, you can start off with the generating function of the Mellin transform and the Mellin transform of the generating function, and you can work out an analytic continuation of the zeta function. And maybe there is something interesting to be said here about the Riemann hypothesis. And the physics interpretation, I don't have to actually tell you. The physics interpretation is the Fielder definition with a truncated theory. So that is why lambda shows up. And that is why you see the lambda parameter in my formulas for pi. And this lambda dependence carries information about the Fielder definition in a truncated amplitude. So for example, if you plotted, suppose you truncated this series here up to 20 terms, and you plotted against log lambda. So log lambda is some convenient way of creating a huge range of lambda. Then what you would see is that this is the expected answer. So this black line here is the exact answer, whereas the red line here is what you would get from the Madhava series. As I told you, the Madhava series converges very slowly. And this is a 20-term truncation. So what happens as you dial lambda is that you see a very long plateau. So remember, this is log lambda, not lambda. So this is up to 10 to the power 6 or something. You see a very long plateau, which actually hugs the exact answer. And then it goes over to the Madhava series. So it actually interpolates between the exact series and the Madhava series. And I should again emphasize that if we did not truncate, so the dependence on lambda is simply showing up because we truncated. If we did not truncate, you keep increasing the number of terms, you will see that the dependence on lambda goes away. So let me show you some fun things with Mathematica. So I think I'm doing very badly with time. Okay, not too badly. Okay. So for instance, you set S1 to be these values, -12 and -12, and you are expected to get pi. You can take your series, the new series that we have. So instead of lambda, my Mathematica notebooks have alpha in it for historical reasons, because we were using alpha when we started working on this, but alpha here in this is literally lambda. So you take 50 terms and you work out 20 decimal place or 20 significant figure accuracy. You will see that you get exactly what you expect from the exact answer. And then you can do more. You can actually dial this lambda, and you see how the values fluctuate. They're expected to fluctuate because you're truncating. But you can see that this is the origin of the plateau, because the fluctuation stops beyond a certain decimal place. So above a certain decimal place, you see these fluctuations. These numbers here, for example, it fluctuates between 4, 5, and 6. But below that, all the numbers have converged. And as I told you that for specific choices of lambda, you can do the sum exactly from 0 to infinity, and it expectedly produces pi. and you can go wild with this. You can actually calculate pi to 500 decimal places, and you see that the expected answer, and of course Mathematica has other ways of calculating pi up till 500 decimal places, all agree. So everything is working as we expected. So here is a comparison, say for between pi's and various zetas. And this is the standard series. By standard series, I am talking about the Madhava series for pi and Euler series for the zetas. And if you truncate to 50 terms, you really get lousy accuracy with the standard series, whereas using the new series, truncating would give you a pretty good answer. So as I mentioned in the beginning of my talk, I'm not trying to sell this as giving the fastest convergence. This is obviously not the fastest convergence. There are beautiful series representations. For example, there is something that is called the Ramanujan representation for pi. He did not work out the representation for pi. He worked out representation for 1 over pi, which actually converge very, very fast. And now it's a different talk how he got that series. But and it is of course fun to ask if the fastest known representation can be interpreted in the language of field theory. But that is not going to be anything that I'll have anything useful to say. And I'll briefly mention about closed string formulas, because we have been focusing on the open string guy. So there are two different approaches to the closed string formula. So one is you can actually work out a 3-channel local crossing symmetric dispersion relation. And this would be the 3 gammas over 3 gamma usual representation for closed string. And you'll get exactly the similar looking decomposition with some interesting changes, some expected interesting changes. So you will see instead of n factorial, you're going to see n factorial square, and you see the poles as they are. This would again be a product of, so it would be a product of 2 Pockhammers now, not a single Pockhammer. And in spite of these square roots, when you actually multiply them together, because of the definition of the Pockhammer, this object is actually a polynomial in S1, S2, S3. There are no square roots. The square roots all go away once you take the product. So together, this is simply a polynomial in S1, S2, S3. Now, this series that I wrote here does not have this parametric ambiguity. You can work out a parametric ambiguity, and we've managed to work out a representation. Now, that has got a few shortcomings, because we use the 2-channel dispersion relation to work out a representation for this kind. And what happens is that you get a piece that is reminiscent of something that looks like open string square, because this is exactly the polynomial that enters the open string amplitude, including the n factorial square piece that actually is exactly the dressing factor that you get in the open string case, now squared, plus this 3rd channel. Now, the 3rd channel does not have a very nice representation, but together you actually get a crossing symmetric answer. So this, I believe that there is a better way of getting a formula for the closed string, but for now, these are the formulas that we have worked out. So now I think I will spend the next 10 minutes on telling you what little I know about string field theory. But before I go there, are there any questions? Because I may have lost you in showing you all these formulas with all these Pockhammers and poles. Okay, so if there are no questions regarding these formulas, let me tell you a little bit about what happens in string field theory. And so the question, of course, is that is string theory different from QFT? And of course, this is a redundant question for you guys. Now, if it was true that you can't do a level truncation in a way that captures up to some accuracy the behavior of the Euler beta function or the string amplitudes by summing over poles, then that would not be a very good thing. So let's try to understand various pieces. So one piece that we would like to try to address is that where is this ambiguity that enters all my representations, this lambda ambiguity, can be motivated from string field theory. In fact, the way that this turned out is that I worked out, we had discussions with Ashok about what is known in string field theory, and that is when we realize that there has to be some ambiguity in the representation of the kind that I've showed you. Now, of course, there are lots of nice modern reviews. Harold is one of the authors, and Harold has a nice book on superstring field theory as well, which is very useful. So first, let me talk about what is happening for the Virasoro-Shapiro amplitude. So in string field theory, you calculate, or you try to calculate this 2-to-2 scattering using a method called the plumbing fixture. So this you can open Bolchinski's textbook, go to chapter 9, and it's explained there what it is. And when you use plumbing fixture, you glue two spheres together. You have 3 marked points, and then there is you take 2 of these spheres and you open up one of the spheres, and you open up the second sphere and join them up with the tube. And then you have to make choices of coordinates for the local choices of coordinates around the tube. And after doing all kinds of Mobius transformations, there is one parameter ambiguity that is left over. There's a parameter lambda. So lambda is a free parameter which has to be bigger than 3. This constraint 3 comes because otherwise you would get overlapping. You would count multiply the regions in the moduli space. And then you have a gluing condition, which actually tells you how you glue these 2 spheres together. That gives you this parameter q. And the question that you then ask is that just using these the S channel, T channel, and U channel diagrams, can you cover the entire moduli space? And it turns out that the entire moduli space cannot be covered. There is a white region that is left over. And this was known historically for a long time. But Ashok in his 2019 paper actually showed how these 3 channels emerge as boundary terms, and the contact term emerges by doing a finite integral in this white region. And these contact terms, he obtained them numerically, and as far as I know, nobody has managed to find an analytic formula for these contact terms. And this lambda dependent ambiguity is, I believe it is similar to this lambda dependent ambiguity that we found in our formulas. So what happens is you write down a regularized version of the propagator. So you introduce some cutoff in the propagator when you're doing the calculation, and after doing this propagator regularization, you choose a particular value of lambda in the choice of coordinates that you did, and you will find that just using the 3 channels, you're unable to cover everything. There is a white region that is left over, and so you do this the integral over the white region numerically, and you essentially get a representation that has the sum of 3 channels, S, T, and U, plus something that is finite, which comes from the integral over the white region. And you can test numerically, but the complaint that I have so far as this approach is concerned is that so far as the integral over the white region is concerned, which is generating the contact terms, there is no truncation, because you're not the integral is finite. There is no concept of a mode there, mode expansion there. So what you can do, the best thing that you can do is you can do a derivative expansion of that integrand and then truncate in the derivatives. So that seems like a little bit of a downer so far as getting a nice analytic formula is concerned. And it seems to me that to evaluate everything analytically, so you have the pole pieces and you have a nice analytic formula for the pole pieces. That is not the important part. The important part is to get an analytic formula for the contact terms. So at least for the closed string, it seems like to be able to do this integral over the white region analytically, you need to find a nice conformal transformation that maps these 3 disconnected disks to concentric regions. And to the best of my knowledge, and this is something that the experts in the audience now can correct me, this apparently is not known. But if this was known, one would be able to do the evaluation of the bulk integral analytically. So this is my understanding of where the closed string field theory reproduction of the Virasoro-Shapiro amplitude as a sum over levels stands. Then you can ask, what about open string? So you could actually take Wheaton's string field theory, and but even here, level truncation seems quite difficult. So in fact, the attempt that I'm familiar with, and again, the experts in the audience, you should correct me, is this attempt by Washington Taylor in 2002. And even when you do the level one, the answer using the string field theory is only has been possible numerically. So let me just.
I don't think it's correct. I mean, why
Yes.
do you say it's numerically? You can just get some like some rational number times square root of 3 sort of things for the interactions.
I was talking about the expansion of the Virasoro-Shapiro amplitude as sum over levels, and I was asking the question whether the contact terms in the answer can be derived analytically. So the kind of formula.
That, yeah, that cannot be done in closed strings, but in open strings, I mean, there's only cubic term. Do you have a contact term as well? Do you add stubs to that?
No, so yeah, right. So in the open string case, so we have to be careful about what we mean by contact terms. In the field theory answers, what I meant by contact terms is not the contact terms that that string field theorists use in the when they talk about Wheaton's open string field theory. So my definition of contact term was literally the residue divided by pole and plus whatever is left over is a polynomial, and that polynomial I'm identifying as a constant is what I'm calling a contact interaction. Now,
okay, I see what you mean.
Yeah. So
okay, good.
So let me actually tell you what I think can be derived from Giddings's work. So Giddings in 1986 used Wheaton's open string field theory to derive the Veneziano amplitude. So what did he do? So he used clever conformal mappings, and he was able to identify what is the S channel and what is the T channel. So after he did these conformal mappings, he identified the S channel to be just this integral here. So this almost looks like the Euler Beta function. If you integrate it from 0 to 1, that it would literally be the Euler Beta function. But the S channel is the integral from half to 1, and the T channel would be the integral from 0 to half. Now the half to 1, you could say that since this is the S channel, let us make the S channel poles manifest, and you can do that. So you could do an appropriate Taylor expansion, integrate term by term, and you'd get an answer. And the resulting answer, and you should actually see, because there is this where is I epsilon in string theory paper by Wheaton, which actually discusses whether you could have done this this kind of a split. So of course he explains it completely differently, talking about the Pochhammer contour and so on. But what you could do is you take this split, you split your Euler beta function into two pieces, integral from 0 to half and half to 1, and then each piece you Taylor expand appropriately and make the appropriate channel pole manifest. Now you can do that, and you can actually convince yourself by playing around that the resulting expression does not have a good behavior in the hard scattering regime. So hard scattering regime means when you're actually doing a fixed angle scattering. So T by S is finite, and both T and S are large. S is large and positive, T is large and negative. And of course, you could do you could actually examine the amplitude for unphysical scattering as well. But it simply does not have a good behavior at the hard scattering regime. And also another disturbing feature of this way of doing it is that it is not clear how to truncate the series, as the poles would now be dressed by this kind of a 2 to the power minus s type factor. And so if you expanded around the pole, you would actually get an infinite number of contact terms. And because of this 2 to the power minus s1 factor, it's obvious that this kind of a series would struggle to converge if either s1 or s2 was less than 0. And a little worryingly for me, and a little the reason why I'm a little dissatisfied with this way of understanding it is that we don't see the appearance of this parameter, this lambda parameter that played a role in my answers, in the truncated answer. And we would like this, and it will turn out, I will give you a table in a bit, you'll require many more modes and derivative order, and hence will not be what you would like to call a field theory. But maybe these difficulties are not insurmountable, and maybe this is something that is addressable with some of the modern attempts in thinking about string field theory. So this is almost my final slide. You could actually do this comparison of the Euler beta function. So the Euler beta function, let's suppose we are inside this joint disk S1, absolute value of S1 and S2 are both less than 20. So you would want to actually ideally truncate up to 20 or maybe 21, 22 modes, but not really keep 100 modes or 1000 modes. Then let's say, as an example, let's put S1 to be 17.1 and S2 to be -2. This is the expected answer that comes from the gamma function form. And if you use this kind of a series that I just explained to you, you get a nonsense. You get a nonsensical answer. You get -844. And to get close to 0.003, you require 100 terms, which is much bigger than, it's a factor of 5 bigger than 20 terms. So this is not really the best representation possible. So in using the new series representations within 20 terms, you get the similar answer. And you can play around with similarly for other values. This is another example where you require 50 terms to get the same kind of a 10 to the power -8 accuracy that the new series gives, and the expected answer is supposed to be 0. For pi, so pi is some kind of a low energy observable. At least there are low energy representations where you're choosing S1 and S2 values to be half. So that's what I call a low energy representations. You could actually fiddle around with that. That's an interesting maths exercise to do, where you have a high energy representation for pi as well. But for pi, the agreement is better. So the conclusion is, so what next? So the crux of the matter is that we use new local crossing symmetric dispersion relations to find new QFT-like representations of the Euler beta and related functions. And this gives new QFT-like parametric representations for transcendental numbers like pi and zeta. So the Euler beta function knows about zeta as well as pi. The closed string amplitude actually does not know about pi, because you don't get even zetas, you only get odd zetas in the closed string low energy expansion. And the new representations seem to point at how to write a suitable basis to bootstrap theories with narrow resonances. This is part of where my interest lies, to see if we can use the S-matrix bootstrap and come up with a cleverer basis to bootstrap theories and see where string theory lies. So we are actually presently examining string one loop answers to see if some nice representations arise from them. We have looked at some de-instanton corrections at NNLO orders, and those can be easily rewritten in terms of things that we have found. And it seems like it's of course, this string field theory wasn't designed to answer perturbative questions of this kind, but then if you have a field theory, you would really like to do the simplest scattering amplitude calculation. So it seems like it's a perfectly legitimate challenge to have for string field theory, is to find an analytic expression of the sort presented here, or try to develop new techniques to do so. And maybe, who knows, the answers would be very interesting. They would have faster convergence than the kind that I presented here. So I'll stop there. Thank you for listening, and I apologize for going 2 minutes over time. Oh, this is the last thing, the deformation. So ask me if you are interested. Yeah. And
Okay, so let us thank Aninda for this very nice talk. And since we started 4 minutes late, actually you finished 2 minutes early.
Okay.
Yeah, we have plenty of time for questions. So
Okay.
please go ahead and unmute yourself.
Yes,
and
there's a
ask.
raised hand. Yes. Go ahead. Somebody had raised their hands. I don't know who, but
I mean, I can ask a question in my email. First of all, thanks. This is great talk. Very fascinating.
yes.
So I was wondering, so you talked about this field redefinition ambiguity, right? This lambda. So is it possible that you do like a BV formalism and try to compute scattering amplitude, keeping antifields intact? So because they basically encode this ambiguity in a most general situation, right? And you
Yeah.
know, can you do something like that, for example, in the scalar field theory, to basically see where this lambda is coming from?
You're not talking about string field theory. You're just doing. You're talking about ordinary gauge
No,
theory.
no, I'm just talking about, yeah, or just scalar field theory, even like it doesn't have to be gauge theory. It's just fact that you know, put these antifields back so that you can keep track of the field definition ambiguity as well as some sort of, BVD or ST symmetry.
Yeah, it's possible. I mean, the simple-minded exercise that I did in the beginning, where I had these 2 light fields and 2 heavy fields, that will definitely have this ambiguity, this field definition ambiguity showing up as soon as you throw away the psi2 field, because that's what you're doing, right? If you're truncating, you're basically throwing away those higher poles, and so this is somehow it's a little different from what we do in effective field theory. So in effective field theory, we actually retain the higher modes, and we actually morally we do a Taylor expansion around a suitable point, keeping those higher modes. But
yeah, because
yeah, truncation
one
is,
advantage maybe because you can imagine different type of field redefinition than what you did, right? And that
yes,
will, in
yes,
principle, gives you more dependence on more
yes,
arbitrary parameters.
yeah,
And if
exactly.
you include these antifields, it can keep track of these things in
Yes,
full
that's a good
generality.
suggestion.
That's
That's
what
a
I
good
was
suggestion.
asking.
Yeah, that's a good suggestion. I'll have to think about it. Yes. Yeah,
Okay,
so it could be
good.
that there
Thank
could
you.
be multi-parameter representations, and so I have been searching for parametric representations for zeta functions and pi's. So there is no parametric representation for pi directly. So indirectly there are, because if you have parametric representation for zeta 2, for example, you can take the square root of that and then get a parametric representation in pi. So mathematicians actually know some parametric representation for zeta functions, but not for everything. There is no systematic parametric representations that are known. So that seems like an interesting maths question as well.
Yeah, another possibility is that looking at the periodic strings, looking at their associated beta functions
Yes.
to do that.
Yeah, that's an excellent
Right.
point. Yeah, indeed. I mean,
Okay.
so since nobody's asking me anything, so can I ask you, do you go by Firat or do you go by Atakan?
I go by Atakan. It's my first name.
Okay. Okay. So
Rather
sorry.
my last
Yeah.
name. No, it's fine.
Are there any other questions? Well, if not, let us thank Aninda again.